The next section of this unit is concerned with what is called power. Power is another one of those words like work and energy that we tend to use in everyday language, but of course power has a precise mathematical meaning. Let me give you a basic description of what is meant by power. Okay, first of all, just in terms of a qualitative definition, power, very simply, is the rate at which work is done. Now, when work is done, energy is used, so then therefore, equivalently, you can think of power as the rate at which energy is used. The key word here, however, is rate, because whenever you are talking about a rate, you're taking a quantity and you're dividing it by time. In this case, we're basically taking work and we're dividing it by time. Now, there are two ways to think of this mathematically. There is, first of all, an average calculation over a large time interval, and then there's an instantaneous calculation over an instant in time. Let me first of all describe the average value. So now here is average power. Okay, average power is referred to as P with the bar symbol, and by definition it's equal to the work done by the force and then divided by the time interval over which that force acts. Now, the numerator of the expression, of course, is our dot product. If you're talking about constant forces, it's just the dot product between the force vector and the displacement vector. Like so. And now what we're dividing by here is the time interval, which I'll refer to as delta t. This is once again the average quantity over a large interval of time. But now let's describe the instantaneous quantity. We'll do so by taking a limit as the time interval delta t becomes infinitesimally small. Let me do that here on the lower board. So now here's the instantaneous quantity. Instantaneous power. So now the instantaneous power is just referred to as P. It's the same thing as the description above, but now we just take a limit as the time interval approaches 0. That is like so. Now, for those of you that are enrolled in the algebra-based course, Physics AB, of course, we don't do any derivatives in that class. But you should recognize that right here in this description is the following. The limit of time approaching 0 of change in position over change in time. That's instantaneous velocity. That's the instantaneous velocity v. However, those of you enrolled in Honors Physics AB or in AP Physics C, you would see this quantity here written as a derivative. You would see this as the following. Derivative of position with respect to time. Derivative of position with respect to time is velocity v, the instantaneous velocity. So regardless of the case as to whether or not you're seeing this algebraically in Physics AB or as a derivative in the other classes, ultimately instantaneous power is the dot product between the force vector that's applied to the object and its instantaneous velocity v at that point. Once again, for those of you that are enrolled in a calculus-based course, you could also describe instantaneous power as the infinitesimal rate at which the work is done divided by the infinitesimal amount of time. Same situation, same expression. Okay, now before we move on to problems, this is, of course, a new quantity for us, so let's just go ahead and check the units. Okay, when it comes to the units, of course, usually what's most important is the metric SI system. Okay, in the metric SI system, we're basically just taking work and dividing it by time, so that's joules divided by seconds. A joule per second, however, is given its own name. It's referred to as a watt. It's named after a 19th century electrical engineer. These are referred to as watts. So for example, let's say you're operating, as we say, a 60-watt light bulb. What that means is that 60 joules of energy are required per second in order to keep the light bulb lit. Now this is the last topic, by the way, where the old imperial or English system of units is important. In the old imperial or English system of units, even though we never did any problems associated with it in lecture or in homework, work and energy is in terms of foot-pounds. And then we're taking a foot-pound here and we're dividing it by time in seconds. And this is just referred to as a foot-pound per second. The reason why this is being mentioned, however, is because of an old archaic English unit that we still use today. Specifically, we use it usually in the context of the internal combustion engine, for example, associated with automobiles, and this is referred to as horsepower, which is abbreviated as HP. The term horsepower dates back to pre-industrial times. It basically refers to, in an agricultural situation, what a beast of burden such as a horse can do when working on a farm or something like that. We have since quantified, however, 1 horsepower precisely, and it's equal to the following. It's equal to 550 foot-pounds per second. It's also the equivalent of 746 watts. Now, you don't need to know these conversions off the top of your head or anything like that, but ultimately, especially for those of you that are into cars, in one of the examples that I'll do, I'll give you a basic understanding as to what is meant by a foot-pound, or excuse me, by a horsepower. Okay, before I do, however, I also want to mention one other thing regarding the units, and this is specifically for those of you that are perhaps enrolled in AP Environmental Science, and that is the term kilowatt hour. Kilowatt hour, which is abbreviated as a kWh. A kilowatt hour is not a unit of power, it's a unit of energy. Specifically, it is usually used to describe electrical energy consumption. So for example, let's say you take a look at your family's electric bill. If you've ever done so, you may notice that the amount of energy that your family used over the course of the month is not given in terms of joules, instead it's given in terms of kilowatt hours. By the way, for those of you who have never looked at your family's electric bill, believe me, you will start to do so once you start paying it yourself. At any rate, however, a kilowatt hour, as I said, is a unit of energy, not power, and here's how it works. Okay, first of all, kilo. Kilo means thousand. So 1 kilowatt hour is 1,000 watt hours. Okay, and now a watt from just a few minutes ago is joules per second. And then we're multiplying it by an hour here, which is 3,600 seconds. 60 times 60, like so. Notice that the seconds cancel out, and you end up then with 1,000 times 3,600, which is 3.6 million joules. Like so. So a kilowatt hour is a large amount of energy and is typically associated with electrical energy consumption. So when you look at your family's electric bill, you're not going to see the amount of joules that you've consumed over the course of the month because it would be a huge number. Instead, you're going to see what's referred to as kilowatt hours. Okay, now when it comes to this topic on power, we're going to keep it basic and we're going to keep it simple. We'll just take a look at a couple of simple situations involving my examples in the next lecture.